Hi, I'm Shane Moore, Technical Service Engineer for PAVCO. First, I want to thank you guys for allowing me to come speak today about bulk processing of trivalent electrodeposits. So let's get started. So exactly what are we talking about here? Well, it's trivalent chromium that can now be applied in a barrel application. Prior to this technology, it was only able to be applied by rack application. But now we've developed a new technology to where it can be applied in a barrel. So just to give you a little history on chrome plating and how it was developed, back in 1920, a man named Dr. Sargent was working in his research and development lab at Cornell University. He published a paper theorizing how chrome plating could be successful, how it could work, but was never actually able to be successful in plating it himself. So in 1924, Dr. Fink and Dr. Eldridge from Columbia University, they took his theories and built upon them and were actually able to be successful in electroplating chromium. The beginning, it was mainly just used on car parts, on motorcycle parts, and that was pretty much it back in the 20s. Fast forward to the 1960s, trichrome was developed, trivalent chromium was developed. In the beginning, it wasn't a very viable process, it wasn't very stable. It turned dark, and it just wasn't a very stable system. Struggle in the beginning of the birth of trivalent chromium. But then in the 70s, chemical manufacturers and R&D centers were actually able to make it much more stable and were successful, and it was commercially available in the 1970s. The first ones were chloride-based chromium. Today, we have chloride-based, sulfate-based, and the barrel application, which is also sulfate-based. So in the beginning, where we were able to develop this new technology, it had been tried, trivalent chromium in a barrel had been tried many times with very little success. You had to have special equipment. Only small loads were possible. Just because of the breaking contact. And it wasn't even a barrel, it was actually more of a basket. So you would put this small load of parts in, and then you would tighten down the lid to the basket onto the parts, and then you would apply current. And the problem with this is that only the parts on the outside the basket, in the outer part of the load were able to see the current. So that's the only parts that really got plated. The parts in the center were kind of shielded by the outer parts, so most of those got very little to no plating at all. It had been tried. Hexchrome had been tried in a barrel. Trivalent chromium had been tried in a barrel. It was only able to be successful when you did this, and you can obviously see the limitations involved there. So there are parts that have to be barrel plated, either because they can't have any rack marks. They need, the thickness distribution from the high current areas to the low current areas has to be small for many different reasons. After the nickel, some of the chemical manufacturers had developed alloys that were similar in color to chrome, but lacked most of the other characteristics of chrome. These were tin nickel, tin cobalt, which is probably the most, I'd say it's the most popular that I've seen in the field. There's also nickel tungsten, which isn't very popular, but it is available, and white bronze. Since tin cobalt is the most popular one, that's the one that I'll be kind of comparing the trivalent chromium in the barrel to, as far as the characteristics, the corrosion resistance, and things like that. Like I said, with these are alloys. There's actually no chrome in these alloys. It was just developed as an alternative to chrome that you could plate in a barrel. The new system, though, actually is chrome. It's actually chrome metal that is being deposited in a barrel application. So it's not one of these tin-containing alloys. Some of the advantages are, like I said, it eliminates the problems with the non-chrome alternatives, especially with tin, because tin tends to develop stannic tin. It precipitates out. You have to constantly add it back. So your alloy is out of balance. Most of the alloys are very pH sensitive, so you can actually change the color of the deposit by allowing the pH to fluctuate or the temperature to fluctuate. They're not quite as stable, and it's hard to keep it as consistent with the alloy type. Also, tin cobalt all the tin-based ones really are very soft, not very corrosion resistant. Actually, functionally it is, but we'll see. We'll talk about this later in more detail, but it seems to darken almost immediately after being exposed in a cast chamber or neutral salt spray chamber. It's very soft, so it's easy to scratch. So it's not really a good alternative. But of course, that was the only thing that was available until this new technology. So some of these other alloys have strong chelators, which makes it much harder to waste treat because it likes to chelate the metals that you're trying to precipitate from your waste treatment effluent. So we have problems there too. The advantages to the barrel application: reduced labor. That's one of the main benefits. No more racking and unracking parts. I've been in some shops where they would stand there for hours just racking each part one by one. But now you can just dump them all into the barrel, close the barrel, and let it go. Much more efficient. We estimate about 10% the labor cost of rack chrome, just because, like I said, that scenario that I saw, racking these real tiny parts and versus pouring them all into a barrel. Also, around 30% the total cost of hexavalent chromium. Not only can you plate it all in the barrel versus the inefficient racking. If you look at everything involved with hexavalent chromium, the governmental guidelines, the waste treating, the toxic effects of hexavalent chromium, if you put all of that together, that's how we came up with this, around 30% the cost of hex chrome, because this is really actually with any trivalent chromium. When you look at just the chemical costs are going to be a little higher than the hexavalent chromium. But when you look at all the other things that come along with the hexavalent chromium, it's actually cheaper to go with the trivalent chromium system. Much safer. Okay, some of the other advantages: no more rack marks. There's no rack marks at all. It has excellent low current density coverage. We actually cut a part open and we're able to measure it was a socket, just a small socket. We cut it in half and it got complete coverage from the high current density to the low current density area, all the way down into these deep recessed areas. It also has a very improved thickness distribution because the current applied is so much more consistent from the high current density area to the low current density area. It's a lot tighter. It's a smaller difference between the high current density thickness and the low current density thickness. Actually, this is I'm looking at slides here. This is showing a part bisection where we actually cut it and cut it open, and we're able to measure the outside and the inside, and it was completely covered. Talk a little bit about color comparison. The color is actually measured on an instrument called colorimeter. And you have L value, A values, and B values. The L and the B are the main ones that we're really concerned with when we're talking about comparing different chromium systems. The L, the higher the number, the whiter the deposit. So L value of 100 is completely white. L value of 0 would be completely black. The A is red to green, so that doesn't really matter when you're talking about chromium. And then there's the B value, which is also very important. It's how blue or how yellow it is. The lower the B value, the more blue in color it is. So when we're talking about hexavalent chromium, it's consistently L value, how white it is, between 82 and 84. The B value is pretty consistent at -1 to -1.4. So this is going to be the bluest color. The next in line is the sulfate trivalent chromium in a rack. So it's going to have an L value of just a couple of marks lower, and sometimes it's really hard to tell the difference if they're say this far away, and then by the time you get here side by side, sometimes you can tell, sometimes you can't. So it's very close in color to the hexavalent chromium. Its L value is around 80 to 82, and B value -0.3 to -1. So it's really close in color to the hexavalent chromium. The barrel sulfate trivalent chromium has a little lower L value, 78 to 82, and a little higher B value, 1 to 2, but it's almost the exact same color that you get with a trivalent chromium deposit. Chloride-based trivalent chromium, it's also pretty close to hexavalent chromium color, but it's not quite as blue, not quite as white. It's very close. It's almost hard to tell by the naked eye unless they're side by side. So it's going to be the darkest and not quite as blue as the hexavalent chromium. The corrosion performance, neutral salt spray. The nickel plays an important role in the corrosion resistance. we found that duplex nickel you can have a thinner deposit of duplex nickel and still have better corrosion resistance than a much thicker deposit of one layer of nickel. A single layer of nickel, you can get about 24 to 48 hours of neutral salt spray to red rust. With a duplex nickel, if it's the same thickness, you can get 96 to 200 hours. So like I said, a thinner layer of a duplex nickel system will have more corrosion resistance than a thicker layer of a single bright nickel layer. Sometimes with automotive companies, with motorcycle companies, they want the maximum amount of salt spray hours. So usually that's when they're asking for 400 hours at least to red. If this is the case, then you would have to go with a quad, it's called a quad nickel stack. So it begins with a semi-bright nickel, then a high sulfur nickel, then a bright nickel, microporous nickel, and then the chromium layer. So that's going to give you your absolute maximum corrosion resistance. So we did some corrosion comparing on just the effects of the chromium deposits. So what we did was we plated duplex nickel on a bunch of parts. They're all the same parts. We tried to get them as close in thickness as possible, which we did. It was around 20 microns total. And then we processed some through the beryl sulfate trivalent chrome, tin cobalt, the hexavalent chromium, chloride trivalent chromium, and the sulfate trivalent chromium. And we put all these in the neutral salt spray chamber just so we could see how just the chromium would affect the corrosion resistance. And we also did it with a cast chamber just to see what the difference was there as well. So what we saw was that they all performed pretty well in the salt spray chamber, all except for the beryl tin cobalt. Other than that, they all performed roughly about the same. And the reason for the beryl tin cobalt, it has the tin-rich deposit, the tin-rich alloy. It was pretty soon after we added this to the cabinet that it went dark almost immediately. So that didn't get a very good rating. Okay, and then like I said, we repeated the test, but this time we put it in a cast. It's a copper acetic acid accelerated test, similar to salt spray, but a little more aggressive. Chloride trivalent chromium and the beryl sulfate trivalent chromium actually did much better than the sulfate trivalent rack, hexavalent rack, and the tin cobalt, of course. I think that's because that the deposit is actually microporous as plated in the chloride trivalent chromium and in the beryl sulfate. So you can't stop corrosion, you can only guide it and direct it. So what the microporous deposit does is instead of it going straight down to the substrate, it disperses the corrosion over many different sites. So that way it spreads it out and it takes much longer for the corrosion to get all the way down to the substrate. Okay, and we also wanted to see how the hardness of the deposit compared. We plated more of these parts again, and we sent them to an outside lab to get evaluated. It is called a nano indentation. It basically indents and it measures the force of which and what we saw was that the sulfate trivalent chromium rack application was actually the hardest. It came in at 1,188 Vickers. Next in line was the hexavalent chromium, and it was just under the sulfate trivalent chromium. And this has been verified many times. We've actually done this test many different times, and it always comes back as trivalent chromium sulfate based in Iraq was actually harder than hexavalent chromium. Kind of surprising, but it was repeated many times and verified. So next under that is chloride trivalent chromium. It comes in at 800, which is just a little less than the hexavalent chromium, but we have many different customers that are using the chloride-based trivalent chromium on hand tools and some other things, and the hardness spec, it meets their hardness spec, so it's definitely hard enough. The beryl sulfate trivalent chromium came in just under the chloride trivalent chromium, so it's still a pretty hard deposit. And then of course the tin cobalt, it came in very low at 382, and that's just because of the tin rich alloy. and so it's easy to scratch, it's easy to dent, and it's just a much softer deposit and not quite as resistant to just a few other comparison characteristics. The chrome metal and the barrel application, it runs around 4 grams per liter, so that makes it much easier on waste treatment, especially when you compare it to hexavalent chromium, which runs at 150, 175 grams per liter. The anode type, you have to have, it's called a mixed metal oxide. It's a coating that goes over titanium, and we have some approved sources. We really highly recommend that we use these suppliers that we have approved, just because the thinner type and the older technology MMO coated anodes would not last very long, and they would start generating hexavalent chromium. But the sources that we have identified as having the best anodes last a very long time, unless they're damaged. If something hits them or damages the coating, then it can be an initiation site to start generating hex chrome. Usually what I've seen is they put some type of barrier between the parts and the anodes so that the current can still flow, but it protects it from getting hit by something. If a rat crashes or anything like that happens, if you scratch that anode, then it's you're gonna have to have it recoated, and that can be expensive. As far as the covering power, the best is the trivalent chromium barrel application. Has the best low current density coverage. Rack sulfate and rack chloride have good coverage as well. Chromic acid, it doesn't throw down into the low current density very well. So the good thing about with trivalent chromium is that with a better coverage, you can have more parts on the rack. Since we're mainly focusing on the barrel application, then we'll stay with that. And it does have excellent low current density coverage. Waste treatment is pretty easy. It's like waste treating a nickel bath. You don't have to do the hexavalent chromium reduction like you do with hexavalent chromium. It's basically like nickel, and like I said, it's only 4 grams per liter of chrome, so it's much easier to waste treat. The toxicity is extremely low. It's nothing like hexavalent chromium. So let's talk about the deposit rates. So with the barrel sulfate trivalent chromium, when it was first developed, we had to have about a 30-minute immersion time, a 30-minute plating time, to be able to get about 0.25 microns, which is usually what's required. But we have developed the technology to where now it only takes about 15 minutes to get that 0.25 microns. We've come a long way with the technology on that. Sulfate trivalent chromium usually takes about 6 to 7 minutes to get 0.25 microns. Trivalent chromium is usually about half of that, as well as hexavalent chromium. So I've got we did some SEM images and on all of the different types of chromium, the chloride-based, hexavalent, tin cobalt, sulfate-based, and when we took some chem wipes and wiped them to make sure with alcohol to make sure that they were clean before we put them into the SEM instrument. Tin cobalt, the deposit was so soft that in the SEM images you can actually see all the scratches that came about just from using that chem wipe, which is not very aggressive. You can also see in the SEM images that the sulfate-based, you can really see the micro porosity, and that's why it does so well in casts and other corrosion-resistant systems, or cabinets, I'm sorry. The equipment that you need. So like I said, you have to use the mixed metal oxide coated titanium. A polypropylene tank is fine because you're only running at like 43 degrees Celsius. You really need a variable speed barrel, and that's because, especially in the beginning, just at least when you're designing the line, because we have found that that's pretty important, and the success is you want the least amount of making and breaking contact as possible. I mean, it's still successful even if it does make and break contact. It can take intermittent contact, but the less that this happens, the better. So usually we'll recommend a variable speed barrel just until we optimize the revolutions per minute and to get a successful deposit. Like I said, usually we'll do that just in the beginning, especially if you're only going to be running one main type of part, then we'll use the variable speed barrel just to optimize the RPM, and then when the rest of the line is designed, then they can just use, they don't have to have the adjustment, they can just be set to that RPM and engineered around that. Other equipment that's needed, you need mild air, and you also need, well, the mild air mainly is just to mix the chemistry, especially in makeup. When you make it up, you need that air to help circulate or to help dissolve all the chemistry. Before startup, you'll want to turn the air on just to mix and make sure that all of the additives are homogeneous. And let's see, you need tank filtration, and you also need the ability to carbon treat because the bath does have organics in it. And with that, as they break down from electrolysis, then you want to be able to have the ability to remove that organic contamination. You want a good filter that can turn over the tank in maybe actually about 2 to 3 times per hour. Will keep the bath clean. Purification by ion exchange, especially if you're running parts that are copper or copper alloys or zinc type substrates like zinc die-cast. You really need to have an ion exchange column for that. And the good thing about the ion exchange resin that we sell is that it actually is it has the highest affinity for copper. So as soon as the copper is introduced into the bath, then ion exchange resin removes it immediately. This is very important because the copper is the biggest contaminant, and it has the most sensitivity to copper than any of the other metallic contamination. For nickel and iron, as long as you have the ability to dummy electrolyze scrap parts or whatever, then that's usually enough to contain the nickel and iron. Because this bath is very tolerant for nickel and iron, but not very much for zinc and copper substrates. We also recommend that the anode rails are plated with nickel before the anodes are installed, just to make sure that, as you bring the barrel over the copper anode bars, then that could dissolve some of the copper, put that in the tank, and we don't want that. Operating parameters, like I said, 4 grams per liter of total chrome. pH, we run around 3.6 is the optimum. Temperature, 43 degrees Celsius. Cathode current density, around 1 to 1.1, 1.2 ASD if possible. The anode current density, whenever you're designing the tank, you want to make sure that the anodic current density stays below 5 amps per square decimeter. And this is because that'll allow the coating to last longer. And sometimes if it's over 5 ASD for an extended period of time, then hexavalent chrome can actually be generated, and we definitely do not want that. Field results, we've had many installations all over the world. I've been involved in some in Asia, Southeast Asia, in the US, and many of those are, well, I can't say the name of the customers, but you would definitely recognize their names. And they've been very successful and very happy with it. We have been successful with plating over electrolysis nickel. The only thing with the electrolysis nickel is that you have to prevent the hypophosphite from getting into the tank through a rinsing, because it seems to be a contaminant for it. But as long as the rinsing is good, then you can plate the barrel chrome over electrolysis nickel as well. So it's a very stable system. It's easy to run. You just run wholesales. There's a couple of titrations, things like that, just to maintain. And then if you set up everything on automatic feeders, then you really don't have to worry about it. It just goes. It just plates and plates. It's a very stable, very good system. So in conclusion, the barrel system has excellent throwing power, good coverage down to low current density areas. Reduced labor cost, of course, because you're no longer racking each little part, you're just dumping it into a large barrel. There's an improvement in production. It has no rack marks, it's consistent color, and it's proven reliability, because we've had so many successful installations that are still running, and they say this is a very simple operation to maintain. So as long as you keep the metallic contamination out of it, as you build organic contamination, you remove that with some carbon. Maybe run a wholesale occasionally, and just make all the ads based on amp hours. Most of our customers use auto dosing. Then it can be a very simple system, and very economical, and you will be as happy as all of our customers are that are running this system. All right, so once again, I want to thank you for your time. Thank you for the opportunity to speak, and I hope everyone has a great day. Thank you.